A four-stroke engine is an internal combustion engine in which the piston completes four separate strokes which comprise a single thermodynamic cycle. A stroke refers to the full travel of the piston along the cylinder, in either direction. The four separate strokes are termed intake. This stroke of the piston begins at top dead center. The piston descends from the top of the cylinder to the bottom of the cylinder, increasing the volume of the cylinder. A mixture of fuel and air is forced by atmospheric pressure into the cylinder through the intake port. Compression: with both intake and exhaust valves closed, the piston returns to the top of the cylinder, compressing the air or fuel-air mixture into the cylinder head. Power: this is the start of the second revolution of the cycle. While the piston is close to top dead center, the compressed air fuel mixture in a gasoline engine is ignited by a spark plug and gasoline engines, or which ignites due to the heat generated by compression in a diesel engine. The resulting pressure from the combustion of the compressed fuel-air mixture forces the piston back down toward bottom dead center. Exhaust: during the exhaust stroke, the piston once again returns to top dead center while the exhaust valve is open. This action expels the spent fuel-air mixture through the exhaust valve. History: Otto cycle. Nikolaus August Otto as a young man was a traveling salesman for a grocery concern. In his travels he encountered the internal combustion engine built in Paris by Belgian expatriate Jean-Joseph Etienne Lenoir. In 1860, Lenoir successfully created a double-acting engine that ran on illuminating gas at 4% efficiency. The 18-liter Lenoir engine produced only 2 horsepower. The Lenoir engine ran on illuminating gas made from coal, which had been developed in Paris by Philippe Lebon. In testing a replica of the Lenoir engine in 1861, Otto became aware of the effects of compression on the fuel charge. In 1862, Otto attempted to produce an engine to improve on the poor efficiency and reliability of the Lenoir engine. He tried to create an engine that would compress the fuel mixture prior to ignition, but failed as that engine would run no more than a few minutes prior to its destruction. Many other engineers were trying to solve the problem, with no success. In 1864, Otto and Eugen Langen founded the first internal combustion engine production company, N.A. Otto & C. Otto & C succeeded in creating a successful atmospheric engine that same year. The factory ran out of space and was moved to the town of Deutz, Germany in 1869, where the company was renamed to Deutz Gasmotorenfabrik AG. In 1872, Gottlieb Daimler was technical director and Wilhelm Maybach was the head of engine design. Daimler was a gunsmith who had worked on the Lenoir engine. By 1876, Otto and Langen succeeded in creating the first internal combustion engine that compressed the fuel mixture prior to combustion for far higher efficiency than any engine created to this time. Daimler and Maybach left their employ at Otto & C and developed the first high-speed Otto engine in 1883. In 1885, they produced the first automobile to be equipped with an Otto engine. The Daimler Reitwagen used a hot tube ignition system and the fuel known as Ligroin to become the world's first vehicle powered by an internal combustion engine. It used a four-stroke engine based on Otto's design. The following year Carl Benz produced a four-stroke engined automobile that is regarded as the first car. In 1884, Otto's company, then known as Gasmotorenfabrik Deutz, developed electric ignition in the carburetor. In 1890, Daimler and Maybach formed a company known as Daimler Motorrad-Gesellschaft. Today, that company is Daimler-Benz. Diesel cycle. The diesel engine is a technical refinement of the 1876 Otto cycle engine. Where Otto had realized in 1861 that the efficiency of the engine could be increased by first compressing the fuel mixture prior to its ignition, Rudolf Diesel wanted to develop a more efficient type of engine that could run on much heavier fuel. The Lenoir, Otto atmospheric, and Otto compression engines were designed to run on illuminating gas. With the same motivation as Otto, Diesel wanted to create an engine that would give small industrial concerns their own power source to enable them to compete against larger companies, and like Otto to get away from the requirement to be tied to a municipal fuel supply. Like Otto, it took more than a decade to produce the high-compression engine that could self-ignite fuel sprayed into the cylinder. Diesel used an air spray combined with fuel in his first engine. During initial development, one of the engines burst, nearly killing him. He persisted and finally created an engine in 1893. The high compression engine, which ignites its fuel by the heat of compression, is now called the diesel engine, whether a 4-stroke or 2-stroke design. The 4-stroke diesel engine has been used in the majority of heavy-duty applications for many decades. Chief among the reasons for this is that it uses a heavy fuel that contains more energy, requires less refinement, and is cheaper to make. The most efficient Otto cycle engines run near 30% efficiency. Both Audi and Peugeot compete in the endurance races of the Le Mans series with cars having diesel engines. These are 4-stroke turbocharged diesels that dominate largely due to fuel economy and having to make fewer stops. Thermodynamic analysis. The thermodynamic analysis of the actual 4-stroke or 2-stroke cycles is not a simple task. However, the analysis can be simplified significantly if their standard assumptions are utilized. The resulting cycle, which closely resembles the actual operating conditions, is the Otto cycle. During the normal operation of the engine, as the fuel mixture is being compressed, an electric arc is created to ignite the fuel. At lower PM this occurs close to TDC. As engine RPM rises, the spark point is moved earlier in the cycle so that the fuel charge can be ignited while it is still being compressed. We can see this advantage reflected in the various Otto engines designs. The atmospheric engine operated at 12% efficiency. The compressed charge engine had an operating efficiency of 30%. Fuel considerations. The problem with compressed charge engines is that the temperature rise of the compressed charge can cause pre-ignition. If this occurs at the wrong time and is too energetic, it can damage the engine. Different fractions of petroleum have widely varying flash points. This must be taken into account in engine and fuel design. The tendency for the compressed fuel mixture to ignite early is limited by the chemical composition of the fuel. There are several grades of fuel to accommodate differing performance levels of engines. The fuel is altered to change its self-ignition temperature. There are several ways to do this. As engines are designed with higher compression ratios, the result is that pre-ignition is much more likely to occur since the fuel mixture is compressed to a higher temperature prior to deliberate ignition. The higher temperature more effectively evaporates fuels such as gasoline, which increases the efficiency of the compression engine. Higher compression ratios also mean that the distance that the piston can push to produce power is greater. The octane rating of a given fuel is a measure of the fuel's resistance to self-ignition. A fuel with a higher numerical octane rating allows for a higher compression ratio, which extracts more energy from the fuel and more effectively converts that energy into useful work while at the same time preventing engine damage from pre-ignition. High-octane fuel is also more expensive. Diesel engines by their nature do not have concerns with pre-ignition. They have a concern with whether or not combustion can be started. The description of how likely diesel fuel is to ignite is called the Octane rating. Because diesel fuels are of low volatility, they can be very hard to start when cold. Various techniques are used to start a cold diesel engine, the most common being the use of a glow plug. Design and engineering principles, power output limitations. The maximum amount of power generated by an engine is determined by the maximum amount of air ingested. The amount of power generated by a piston engine is related to its size, whether it is a 2-stroke or 4-stroke design, volumetric efficiency, losses, air-to-fuel ratio, the calorific value of the fuel, oxygen content of the air and speed. The speed is ultimately limited by material strength and lubrication. Valves, pistons and connecting rods suffer severe acceleration forces. At high engine speed, physical breakage and piston ring flutter can occur, resulting in power loss or even engine destruction. Piston ring flutter occurs when the rings oscillate vertically within the piston grooves they reside in. Ring flutter compromises the seal between the ring and the cylinder wall, which causes a loss of cylinder pressure and power. If an engine spins too quickly, valve springs cannot act quickly enough to close the valves. This is commonly referred to as valve float, and it can result in piston-to-valve contact, severely damaging the engine. At high speeds, the lubrication of piston cylinder wall interface tends to break down. This limits the piston speed for industrial engines to about 10 ams. Intake exhaust port flow. The output power of an engine is dependent on the ability of intake and exhaust matter to move quickly through valve ports, typically located in the cylinder head. To increase an engine's output power, irregularities in the intake and exhaust paths, such as casting flaws, can be removed, and, with the aid of an airflow bench, the radii of valve port turns and valve seat configuration can be modified to reduce resistance. This process is called porting, and it can be done by hand or with a CNC machine. Supercharging. One way to increase engine power is to force more air into the cylinder so that more power can be produced from each power stroke. This can be done using some type of air compression device known as a supercharger, which can be powered by the engine crankshaft. Supercharging increases the power output limits of an internal combustion engine relative to its displacement. Most commonly, the supercharger is always running, but there have been designs that allow it to be cut out or run at varying speeds. Mechanically driven supercharging has the disadvantage that some of the output power is used to drive the supercharger, while power is wasted in the high-pressure exhaust, as the air has been compressed twice and then gains more potential volume in the combustion, but it is only expanded in one stage. Turbocharging. A turbocharger is a supercharger that is driven by the engine's exhaust gases, by means of a turbine. It consists of a two-piece, high-speed turbine assembly with one side that compresses the intake air, and the other side that is powered by the exhaust gas outflow. When idling, and at low to moderate speeds, the turbine produces little power from the small exhaust volume. The turbocharger has little effect and the engine operates nearly in a naturally aspirated manner. When much more power output is required, the engine speed and throttle opening are increased until the exhaust gases are sufficient to spin up the turbocharger's turbine to start compressing much more air than normal into the intake manifold. Turbocharging allows for more efficient engine operation because it is driven by exhaust pressure that would otherwise be wasted, but there is a design limitation known as turbo lag. The increased engine power is not immediately available due to the need to sharply increase engine RPM, to build up pressure and to spin up the turbo, before the turbo starts to do any useful air compression. The increased intake volume causes increased exhaust and spins the turbo faster, and so forth until steady high-power operation is reached. Another difficulty is that the higher exhaust pressure causes the exhaust gas to transfer more of its heat to the mechanical parts of the engine. Rod and piston to stroke ratio. The rod to stroke ratio is the ratio of the length of the connecting rod to the length of the piston stroke. A longer rod reduces sidewise pressure of the piston on the cylinder wall and the stress forces, increasing engine life. It also increases the cost and engine height and weight. A square engine is an engine with a bore diameter equal to its stroke length. An engine where the bore diameter is larger than its stroke length is an over-square engine. Conversely, an engine with a bore diameter that is smaller than its stroke length is an under-square engine. Valve train. The valves are typically operated by a camshaft rotating at half the speed of the crankshaft. It has a series of cams along its length, each designed to open a valve during the appropriate part of an intake or exhaust stroke. A tappet between valve and cam is a contact surface on which the cam slides to open the valve. Many engines use one or more camshafts a row of cylinders, as in the illustration, in which each cam directly actuates a valve through a flat tappet. In other engine designs the camshaft is in the crankcase, in which case each cam contacts a push rod, which contacts a rocker arm that opens a valve. The overhead cam design typically allows higher engine speeds because it provides the most direct path between cam and valve. Valve clearance. Valve clearance refers to the small gap between a valve lifter and a valve stem that ensures that the valve completely closes. On engines with mechanical valve adjustment, excessive clearance causes noise from the valve train. A too small valve clearance can result in the valves not closing properly. This results in a loss of performance and possibly overheating of exhaust valves. Typically, the clearance must be readjusted each 20,000 miles with a feeler gauge. Most modern production engines use hydraulic lifters to automatically compensate for valve train component wear. Dirty engine oil may cause lifter failure. Energy balance: Otto engines are about 30% efficient. In other words, 30% of the energy generated by combustion is converted into useful rotational energy at the output shaft of the engine, while the remainder being losses due to waste heat, friction and engine accessories. There are a number of ways to recover some of the energy lost to waste heat. The use of a turbocharger in diesel engines is very effective by boosting incoming air pressure and in effect provides the same increase in performance as having more displacement. The Mack Truck Company, decades ago, developed a turbine system that converted waste heat into kinetic energy that it fed back into the engine's transmission. In 2005, BMW announced the development of the Turbosteamer, a two-stage heat recovery system similar to the Mack system that recovers 80% of the energy in the exhaust gas and raises the efficiency of an Otto engine by 15%. By contrast, a six-stroke engine may reduce fuel consumption by as much as 40%. Modern engines are often intentionally built to be slightly less efficient than they could otherwise be. This is necessary for emission controls such as exhaust gas recirculation and catalytic converters that reduce smog and other atmospheric pollutants. Reductions in efficiency may be counteracted with an engine control unit using lean burn techniques. In the United States, the corporate average fuel economy mandates that vehicles must achieve an average of 35.5 miles per gallon compared to the current standard of 25 mpg. As automakers look to meet these standards by 2016, new ways of engineering the traditional internal combustion engine could have to be considered. Some potential solutions to increase fuel efficiency to meet new mandates include firing after the piston is farthest from the crankshaft, known as top dead center, and applying the Miller cycle. Together, this redesign could significantly reduce fuel consumption in NOx emissions. See also. References. General sources: Hardenberg, Horst O. The Middle Ages of the Internal Combustion Engine. Society of Automotive Engineers. ISBN A978-0-7680-0391-8. Science World Wolfram Com Otto Cycle HTML, Senjal, Yanis A. Michael A. Bowles. Yeling He. Thermodynamics and Engineering Approach. NP. The McGraw-Hill Companies. ISBN A978-7-121-08478-2. Benson, Tom. Four-stroke internal combustion engine PA National Aeronautics and Space Administration. Retrieved May 5, 2011. External links: U.S. Patent 194047, four-stroke engine animation, detailed engine animations, how car engines work, animated engines, four-stroke, another explanation of the four-stroke engine. CDXE textbook, some videos of car components in action. Video from inside a four-stroke engine cylinder, new four-stroke.